Welcome to this lecture series in linear algebra. In this lecture, we will learn some interesting properties of the minimal polynomial, which will also help us calculate the minimal polynomial of a given endomorphism to some extent in certain situations. And let us recall what we need. So we need to know, of course, what are eigenvalues and eigenvectors. Let us briefly recall what is the definition of the minimal polynomial. The minimal polynomial of an endomorphism T is the smallest degree monic mx. So this is a monic of smallest degree which is satisfied by T. We showed that it is unique, so the use of the definite article is sanctioned. So that's the minimal polynomial. It exists. Most importantly, it exists. All right, and we will need to know what is meant by transpose of an endomorphism and the natural isomorphism between a vector space and its double dual. So once we are given an endomorphism on a vector space V, T transpose is a map from the dual of V to the dual of V. How is it defined? Once we are given something in something, let's call it maybe phi. So this is an element of the dual of V. This is a linear functional on V. So this is in V star. What is its image under the transpose? Its image under the transpose is what you obtain when you compose it by T. So this composite is T transpose phi. So that is the notion of the transpose. And let us look at what was the isomorphism between V and V double star. So the map phi super V, what does it do? It takes a vector to, just by notation, it takes it to this guy. And what is the definition of that guy? It is a map from V star to F. Fine. So it consumes something in V star and outputs something in F. If it consumes phi, it outputs phi of V. So that's the definition of this guy, and the definition of this guy is little v going to that thing. Okay. And what is the natural isomorphism between V and V double star? This is the natural isomorphism between V and V double star. Now what is the naturality? So if we are given an endomorphism between two vector spaces, then the following diagram commutes, where the one here is just the transpose of T. So what this says is that essentially this map and that map are the same under these identifications. We looked at this in detail. All right, so let us proceed. Here are some problems for practice. This one I should mark as star because I'm going to use it. This is not hard, but I'm going to use it. It says something very simple. Suppose we have an endomorphism on a vector space V and W is a T invariant subspace. Then we get an endomorphism on W. This is the restriction of T to W. So this is the map which takes W to T of W. And all we are saying is that for any Px, for any polynomial over the base field, this endomorphism is same as the restriction of this endomorphism to W. This is an endomorphism on V. You restrict it to W, you get the corresponding endomorphism on W when you feed the restriction of T to W to P is same as when you restrict what you get when you feed T to P. So anyway, just read this and you will get what I'm trying to say. But this deduction is very, very simple. Okay. So here is a most important fact. Fix an endomorphism on a vector space V and Mx be the minimal polynomial of the endomorphism. Then the roots of Mx in the base field are precisely the eigenvalues of T. So this is very important that we are taking the roots in the base field. For instance, if our vector space was a real vector space, you get the minimal polynomial, you take its root in the complex numbers, that's not going to give you the eigenvalues of t, that will give you some extra things. So when we take the roots of the minimal polynomial in this theorem, we will take the roots only in the base field. There may be no roots in the base field. For example, as we saw, the rotation of the plane R2, the minimal polynomial of that was x squared plus 1. It does not have any root in the real field, and therefore the operator also does not have any eigenvalues under this theorem. So we want to prove this very beautiful statement. Just give me 1 second. Right. So start with a root of the minimal polynomial, root of mx, and we want to show that lambda is an eigenvalue. Right? So since lambda is a root of mx, we know that x minus lambda divides mx, that is mx equals x minus lambda times qx for some qx. Okay, but what does that do? That implies that mt is t minus lambda I qt. Why is this? Why is this implication? Well, as we saw, evaluation, this kind, I shouldn't say evaluation, but you have mx as the product of two polynomials. We replace x by t on both sides. Of course, we will get equality, but when you replace x by t in this polynomial, you may do it individually and then you compose. So this is what we called well behavior of product under this substitution map, where you start with a polynomial and output an endomorphism on V. You take a polynomial px and output pt. So this takes product fx gx to ft gt, where this is of course the composite of ft with gt. So this is why this equation holds. And now, since mx was the minimal polynomial, this is 0. Right? And now if lambda were not an eigenvalue of t, this would be an invertible linear map, linear endomorphism on V, and hence we would get that this is actually 0. Because if you compose this by an invertible thing to get 0, this must be 0. But if qt is 0, then that means there is a smaller degree polynomial, smaller degree non-zero polynomial than mx, which is satisfied by t. But that would be a contradiction to the minimality of m, because this is also a monic polynomial. I mean, I'm just being very, very precise. So qx is also a monic polynomial because mx is monic, this is monic, so this is also monic. And if this were not invertible, then this would be 0, and hence qx would be a smaller degree monic polynomial compared to mx, which is also satisfied by t, and that would contradict the fact that mx is the minimal polynomial of t. So this implies that this must be invertible. Sorry, this must be non-invertible, and therefore lambda is an eigenvalue of t. The non-invertibility of this is equivalent to saying that lambda is an eigenvalue of t. So I don't want to write all this. I've said it in words, you can write it in your notes. Okay, for the other direction, start with an eigenvalue. Start with an eigenvalue of t. We want to show that it is a root of the minimal polynomial. Root of mx. Okay. So we will use the division with the remainder theorem, or a very special case of it. So what we can say is mx looks like plus some scalar which actually is equal to m lambda for some qx. Right, we are just using a very special case of division with remainder theorem. We saw this, in fact, specifically we saw this also. You have a polynomial, you divide it by this, you get a quotient and a remainder. The remainder is necessarily that, because when you evaluate lambda on both sides, the left side will be m lambda, this will go away, so this has to be m lambda. Okay, so we have this, and now evaluate, or rather substitute both sides. Substitute in place of x t on both sides. So this implies mt equals t minus lambda I qt plus m lambda identity. But mt is 0. Which implies m lambda I equals t minus lambda I qt. Right? But since lambda is an eigenvalue of the endomorphism T, this is not invertible, and hence this cannot be invertible. If you compose something by something that is not invertible, this is not going to be invertible. One way to see it is the following. You just write it this way. This thing is also equal to qt composed with t minus lambda I, and since this is non-trivial kernel, you feed something, it becomes 0, and as a result this is also 0. So this whole thing has a non-trivial kernel, and hence this cannot be invertible, and hence this cannot be invertible. But if m lambda is non-zero, this would be invertible. So the only way this can happen is that m lambda is 0, because otherwise we would have an invertible thing equal to a non-invertible thing. So m lambda must be 0, and hence in this equation we see that x minus lambda divides mx, or even before that, since m lambda is 0, it just means that lambda is a root of mx. So that's it. That's the reasoning to finish the proof in this direction. All right. Again, I don't want to write down all the things that I just said. So this is a very important theorem. Let's keep this in mind. And this is another very important theorem. So suppose we are given an endomorphism T on a vector space V, and we are also given a T invariant subspace W of V. Then we define Sx as minimal polynomial of the restriction of T to W. So the restriction of T to W is an endomorphism on W. All right, so this is the minimal polynomial of this endomorphism. Qx is the minimal polynomial of T bar. Now what is T bar? Since we have W as an invariant subspace, the following diagram commutes. This is something we have done many times. So the endomorphism T gives rise to an endomorphism on the quotient, and this is what we are calling T bar. So Qx is the minimal polynomial of T bar, and Mx is the minimal polynomial of T. So we will say two things. First is that Sx and Qx divide Mx. So the minimal polynomials of restriction and quotient, let's say, divide the original minimal polynomial, and the minimal polynomial of the original thing divides the product of the minimal polynomial of the restriction and the quotient. So this gives a way to nail down Mx kind of recursively. If you can figure out the minimal polynomials over smaller things, you should be able to figure out the minimal polynomial over bigger things. To some extent, maybe this will not completely nail it down every time, but it will point us to the right direction. So in particular, this also says, if you couple it with the previous lemma, that the eigenvalues of T bar are also eigenvalues of T, because Qx is dividing Mx, therefore every root of Qx is a root of Mx, and hence every eigenvalue of T bar is an eigenvalue of T, because roots of Qx are precisely the eigenvalues of T bar, and roots of Mx are precisely the eigenvalues of T. So this is a very important and interesting consequence. Okay, so now let's start proving it. First, we will prove this part. Okay, so to show that Sx divides Mx, enough to show that this is 0. So why is this? We proved a property of the minimal polynomial in the previous lecture. And what was it? Suppose T is an endomorphism on a vector space. We forget about all these things for the moment. If T is an endomorphism on a vector space V and Mx is the minimal polynomial of T, and we have some polynomial fx such that ft is 0, then Mx divides fx. So Mx divides every polynomial that is satisfied by T. We proved this. So to prove that the minimal polynomial of the restriction divides something, this is as of now something, this is the minimal polynomial of T, but in context it is just some polynomial. We want to show it is enough or equivalent to show that this is the case, that the substitution of the restriction in place of x in M leads to the 0 endomorphism. So this is our goal, but if you have solved the star mark problem, we know that this is equal to MT restricted. This is 0 because that is 0, and hence this is 0, so we are done. So this proves, this proves this particular deduction. And to prove that Qx divides Mx, first we will make an observation of this sort in the context of quotients. So it's a kind of a side remark. So let Px in Fx be arbitrary. And we have this diagram. Okay, so you can justify that Pt bar is equal to Pt bar. Now this has to be explained. What does this mean? Pt is an endomorphism on V, and since W is T invariant, it is also Pt invariant, a very simple exercise. And therefore Pt bar is an endomorphism on the quotient. So this diagram actually also leads to a cousin diagram, which let me draw. Okay, so Pt bar is an endomorphism on the quotient, while P of T bar is also an endomorphism on the quotient, and we are saying that they are the same. So take this as an exercise. Again, very simple exercise. And using this, we can prove that Qx divides Mx, because to prove Qx divides Mx, we just need to show that M of T bar is 0. But M of T bar is equal to MT whole bar, which is 0 bar, which is the 0 endomorphism of the quotient, and that implies Qx divides Mx, because Qx by definition is the minimal polynomial of T bar. So we have proven the first part. Okay. So now we will prove the second part, which is that Mx divides this. And again, to do this, we will just show that STQT is 0, because the substitution of T in place of X in this polynomial is same as ST composed with Qt. So we will just show that this is the case. And to do that, first we have a claim. Claim is that Qt of V is in W for all vectors in the vector space V. Why is this? So we have Qt bar equals Qt whole bar, as we just observed on the previous page. But q is the minimal polynomial of t bar, so the left hand side is 0. So we get this, which means what? Which means 0 equals this for all, and maybe 0 bar would be a better notation, which implies, which gives us that QTV is in W. So that proves the claim. And now we want to show that this composite STQT is 0. So feed an arbitrary vector v to it, and if we can show that this is 0, we will be done. So how do we show that this is 0? This is equal to STQTV, but this thing is in W. This thing is in W by the previous claim, and therefore this is equal to ST restricted to W of QTV. So note that we have used our claim here when writing this equation. Okay, but ST restricted to W is same as ST restricted to W, which is 0, because S is the minimal polynomial of the restriction. So this is 0, right? And therefore the answer is 0. So this is 0 for all V, and hence this endomorphism is 0, which implies that MX divides SXQX. Okay. So very important lemma. Let us look at it one more time. We have some endomorphism on V. W is an invariant subspace. Then we get minimal polynomial of restriction. We get minimal polynomial of quotient. And we have the minimal polynomial of the original endomorphism. Then the minimal polynomial of restriction and quotient divide the original one. And the minimal polynomial of original one divides the product of the two descendants. Okay. So as an example, let us compute the minimal polynomial of this particular endomorphism. So it is an endomorphism on C3, defined in this fashion, and its matrix with respect to the standard basis is equal to that. So what is the minimal polynomial of this guy is the question. So first define W as span of E1. So take W as span of E1 and note that W is T invariant. Okay. And what is the corresponding thing on the quotient? So where V is, let's call this vector space V. So we have V mod W as the quotient space and the corresponding endomorphism on it. So you can just verify that the matrix of T bar with respect to the basis that gets induced on V mod W by the standard basis of V, which we can write down. So if the standard basis on V is this, then the standard basis here is B bar, which is E2 bar, comma E1, E3 bar. So this matrix is, just verify as an exercise, is equal to that. So this row kind of gets, this part kind of gets killed. Okay. So I will leave you to check that the minimal polynomial of the restriction, let me just say min poly of the restriction is x minus 6, and the minimal polynomial of the quotient thing is x minus 6 into x minus 7. So how do we come to this conclusion? Well, here you can easily check that 6 and 7 are eigenvalues of T bar. So x minus 6 and x minus 7 must be factors of the minimal polynomial of T bar. And hence, this much is definitely there in the this definitely divides the minimal polynomial of t bar, but if you substitute t bar here, you will get 0. So this has to be the minimal polynomial of t bar. Fine, so we have the minimal polynomial of t bar, we have the minimal polynomial of the restriction, and by the previous proposition, we know that, let's call this Sx, and let's call this Qx. By the previous proposition, we know that Qx divides Mx, and Mx divides Sxqx, which is that x minus 6, x minus 7 divides Mx. Mx is the minimal polynomial of t, and Mx divides x minus 6 square times x minus 7. So the candidates for the minimal polynomial of Mx are this and that. But if you substitute t here in place of x, you will not get 0, while if you substitute t here in place of x, you will get 0. So the minimal polynomial of t is this polynomial. Okay. This is a simple exercise that if you have an endomorphism which is invertible and whose minimal polynomial is, written this way, then a0 is non-zero, and this is the minimal polynomial of the inverse. So this is an exercise. Basically, if we are given the minimal polynomial of an invertible endomorphism, then we can write down the minimal polynomial of the inverse. Okay. And I think one last thing that we should definitely do is that if we are given an endomorphism T, then T and T transpose have the same minimal polynomial. Very interesting fact. So here is a proof. Yeah, so in particular, this says that T and T transpose have the exact same eigenvalues, something that is not obvious. Right? Because we know that the roots of the minimal polynomial are precisely the eigenvalues of any endomorphism. So if they have the same minimal polynomial, they have in particular the same eigenvalues. Okay, so how do we prove this? Let Mx be the minimal polynomial of T, and let us also write it maybe in this fashion. Be the minimal polynomial of T. Okay, so yeah, and let this be the minimal polynomial of the transpose. Okay, now by this equation, this equation, we have 0 is equal to, or one more step, 0 is equal to mt is equal to okay. All we have done is just write t in place of x on both sides. And so 0 is equal to that thing. And now we take transpose of both sides. So we get 0 is the transpose of identity is identity. This is that. And we are just using some basic properties of the transpose. So in particular, we are using the fact that if you take the transpose of square, you get square of transpose, and similarly for other powers, and the transpose distributes over summed endomorphisms, and so on and so on. So we have that, and therefore 0 is equal to m t transpose, and hence the minimal polynomial of the transpose divides the minimal polynomial of the original. T transpose satisfies some polynomial, so the minimal polynomial of the transpose must divide that some polynomial. So we will box it out. Okay, and let's say this is the minimal polynomial of T double transpose. And by the same logic, we can show that this is the case. But we have this natural identification right? We have this natural identification, natural isomorphism between V and V double star with the commutation of this diagram. So we can write T double transpose as this thing. So anyway, philosophically, what does this mean? Philosophically, this means that T double transpose is essentially the same as T. And therefore, the minimal polynomial of T double transpose should be same as the minimal polynomial of T, and that you can prove using this equation. So this implies that this equals mx. And now if you use this here, you will see that mx divides mtx. And we had already concluded that mtx divides mx. Since mx and mtx are both monic and they divide each other, it implies that they are equal. If two monic polynomials divide each other, they must be equal. So this is equal to that. mtx is equal to mx. Okay, so this was a crucial observation. From here we get this equation, and what we are really using here is the following. If we have, let's say, S and T are randomorphisms where S is invertible, then the minimal polynomial of this guy is same as the minimal polynomial of T. This is a very simple exercise, and that is what tells us that the minimal polynomial of T is same as the minimal polynomial of T double transpose. And with the previous deductions, we deduce our theorem. Yeah, so I think this is it. Yeah, this is all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.